Hooke's law and elastic potential energy. Here we go. Next topic in our For You adventure here. Um, so Hooke's law. You have seen this in grade 11, hopefully. Did you? I forget. Oh, anyway, either ways, we're seeing it. It's about the amount of compression or deformation of a spring and what kind of force is required. And it turns out that it's proportional. Okay, so you think of a proportional situation. I'm going to show you this a couple of ways, but basically, if force is proportional to the amount of compression, and so if you divide both sides by x, you'd get a constant value. Right? That's your proportionality constant, the k value, the proportionality constant. And so that's always to do with some kind of physical property of a situation. I'll mention more about that in the next slide. But really, that becomes F equals kx. Okay, so that's just the quick introduction to Hooke's law, the equation, the amount of force on a spring, how much it compresses, and there's this value that's rating, like a stiffness rating for the spring. So, like, where does this come from? Well, you basically would just measure a bunch of forces and how much put a bunch of forces on a spring and measure how much compression there is, right? So turns out when you do this, you get a bunch of values that are a nice straight line for a good portion, and so that's the direct variation we're talking about, and that's where Hooke's law is correct and doing its thing, right? So that's where your slope would be the force over the x. Your slope's your constant value, your k value, right? So that's your proportionality constant. So your k value, your proportionality constant, and like I said, this is a value that's some kind of physical characteristic of the system. It's the stiffness of the spring. Other examples you've seen about that, if you have F equals ma, the amount of acceleration is proportional to the force, and the proportionality constant is the mass, the physical property of the situation that determines how much acceleration there will be is the mass, right? It's a bits of that. And then V equals IR, how much current will flow for a given voltage in a circuit, right? If you divided both sides by I, you'd have this constant value all the time, and that's called Ohm's law. And that's your resistance is your physical property. And with friction, we saw it recently with the coefficient of friction. So the amount of friction is proportional to the normal force. And so if you divide both sides by normal force, you have a constant value, the coefficient of friction, and so on. So hopefully becoming more and more familiar with the idea of just proportional situations and the kind of mathematical relationship you get out of this, right? And so, so obviously here we're talking about a nice straight line. It's proportional to the displacement or the amount of compression and so on. I could even pull in a y equals mx plus b, I suppose, on the fly here. So, the grade 9 version of things, we'd have y equals mx plus b. And so we'd have the force equals the slope, which is our proportionality constant, times the x, and then the b value you can see is 0, and so on, right? So the slope is the k value. So it matches all the things you've seen before. All right. Was there anything missing there? This is the top here where it goes what they call beyond the elastic limit. When Hooke's law starts to break down, you find that the force doesn't keep increasing. And so you stretch an elastic band and eventually it just kind of stretches without the force kind of increasing. It's deforming and going beyond its elastic limit and basically breaking rather than just stretching the way it's supposed to. It can. So we're going to go ahead and look at the elastic potential energy in a situation like this, and then we'll do examples, some calculation examples with both concepts involved. Okay, so elastic potential energy, whatever kind of symbolism you want to use for it here, but that's what I'm using right now, just as long as you're clear that you're talking about elastic potential energy. Energy can be stored in any object that returns to its initial shape after it is compressed, right? So when you're compressing something, really you're doing work on it. You're pushing on it with a force and doing work. So the force is obviously F equals kx if we have something that obeys Hooke's law. And we know energy-wise that it's force times distance. It's the work and the force times the distance, right? So we know the force is kx, and that's our change. That's our elastic potential energy, right? So we'll get kx going in the next slide, right? So if you're compressing a spring, you're storing energy, and then when the spring releases, it's letting that energy back out, and so on, right? If there is friction, which of course there always is in real life, the energy you get out is going to be backwards here. The energy you put in is going to be less than the energy you get out. I don't know why that's small there right now. It's a superscript, subscript, whatever, for some reason. Energy in is a little less than the energy you get out, right? There's always some friction losses, basically energy that just goes to heat or whatever, right? So sometimes, though, of course, to make things easy for calculations, we just pretend things are frictionless and simplify our lives and do some kind of first level calculations, right? So here we go. There's our F equals Kx going in there, right? That thing's not a constant. We know we've got this situation where, recall, I should say here, that if you have force times force and displacement for work done, we can just get the area underneath the graph. Here's the spring compression. The force is increasing, proportional to x, right? So F equals Kx. So that's where we're getting our Kx in here eventually here, right? So we have the force in there, and that's where the Kx is finally going in. Okay, so we have 1/2 of the base times the height, 1/2 of the amount of compression times the force required to do that, and so on, all the way along. Anyway, so that quickly becomes 1/2 Kx squared, which is a really nice result. If you notice the extreme similarity to 1/2 mv squared, it makes it super easy to remember if you already have 1/2 mv squared for kinetic energy memorized and understood and familiar, right? So that is a new relationship, a new equation for you. Elastic potential energy stored in a spring is 1/2 Kx squared. So make sure to emphasize that in your notes or whatever and have that be familiar. So here we go. Practice question. A spring with a force constant of 2 newtons per meter is compressed 0.3 meters. Determine the elastic potential energy stored and the force needed to cause the compression. Just notice here the units for that K value. Force is proportional to, or force equals Kx, right? It's proportional to X. And so that K value, if you're dividing out the X, you'd have newtons per meter, right? So there's that newtons per meter idea, right? It was there. And then if you're looking at this in a different way, just in terms of kilograms and meters and seconds and so on, newtons is kilograms meters per second squared, and you're dividing out meters. So that force constant actually could just be kilograms per second squared, which seems really odd. Newtons per meter is much, much more understandable. In order to displace the compressive thing by a meter, you need a certain amount of force. But it's interesting that the base units simplify to just a kilograms per second squared. It's a weird thing. Anyways, given information, we have the K values 2, we have the displacement or the compression of the springs 0.3, and you just whip out the equation that is to do with the concepts here and plug numbers in, and boom, 0.09 joules stored, right? And then for the compression, F equals Kx, right? So F equals Kx, really that could have been part A, really, I guess, since we talked about it first, but that's the force needed for it. So 0.6 newtons would be needed, and the amount of energy stored in that spring would be 0.09 joules. And another nice kind of example here. If you have a block, 2.5 kilogram block, sliding towards a spring, and then you experimentally see that it comes to rest after compressing the spring 0.1 of a meter, or 10 centimeters, in other words. And so if there's negligible friction in the situation, there you go. There's the, ignoring all the losses. The losses were ignored here too, really. But the question is, what speed did it have? Okay. And so this is, obviously we're going to use an energy concept in this question to make it very easy to do, or way easier than if we didn't, that's for sure. You could, I suppose, talk about, friction. I don't know if you could or not. If we have information like final velocity 0, that kind of stuff. I don't think we have enough information to do it without energy concepts. But the energy concepts are, of course, that whatever the initial form of energy is transfers to the final form. So you could think of it as kinetic as transferring to elastic potential. Or we could look at the idea that the energy is the same all the time in the entire system. And that's your conservation of energy way of looking at things. So either one of those is fine. Okay, please make sure to communicate your solutions well, like this, like either of these. Paragraph went weird on me there. So like just communicate like either of those is fine. If there's multiple forms of energy involved, and if you're including friction and other forms, you'll find the conservation of energy one a little easier to keep track. So yeah, that would just be then essentially saying that the kinetic energy becomes the elastic potential energy. So 1/2 mv squared equals 1/2 kx squared. And you just solve, multiply both sides by 2, whatever you want to do here. I have, the 1/2, there's where multiply both sides by 2 and that got canceled out. Divide both sides by 2.5, take the square root and so on, right? So technically here, plus or minus, right? Plus or minus value on this, but really we're just getting a speed in the end, right? I just like to always show when I'm rooting both sides that technically there's a plus and a minus answer that are answers that are equally valid mathematically. Oh, look, I had it there. I was ahead of myself. But in the end here, we're just saying, okay, well, it got a certain speed, right? So, or it had a certain speed, I should say. Yeah, so there you go. That is Hooke's law and elastic potential energy. And let me know, as always, if you have any questions. And there was a video in here, I didn't mention it as I was going through. If you want to watch it, yeah, it just describes the kind of stuff we just went through. If you want to see it again or whatever, but I had that video in there for when these lessons were used independently without these YouTube videos. So we did it ourselves. All right, there we go. As always, thanks for watching.